Alright, so let's find this volume. Find the volume of the solid region bounded by the paraboloid z equals 4 minus x squared minus 2y squared at the xy plane. And let me show you the figure that's given. And if we had our calculators, we could graph this in the TI calculators. So the xy plane just means that it doesn't continue to go down any further than, I guess, z equals 0, or the xy plane. Okay. So if we let, and z is f of xy, right? So z is the same as f of xy. If we let z equal 0, then we would have let z equal 0 and then shift some of these terms around so it would be in more of a standard form. Something like x squared, see, then plus 2y squared equals 4. And so in 2 dimensions, you can see that would be an ellipse. And if we were just looking, let's say that we took the top of this figure here and we pulled it to where the pole, where the z-axis was facing us, and we looked down, we would just see that ellipse there. X squared plus 2y squared equals 4, which that's not the standard form of an ellipse, but you could figure that out, I think, if you had to. Okay? And so if we want to set this up dy dx, volume equals the double integral, and then we want let our dA equal dy dx, dy dx. Then first we want to bound our y variable. So take this equation where we let z equal 0, and let's bound or figure out the bounds for our y variable. So if we were to take and solve this for y, we would have y squared equals 4 minus x squared over 2, right? If we move the x squared over, divided both sides by 2, then we solve for y by taking the square root, which would mean we put a plus or minus here. So your y is going to be in between the negative square root of 4 minus x squared over 2 and the positive square root of 4 minus x squared over 2. Alright, and so that's how we find the bounds for our y variable. And since we were wanting to set this up dy dx, that's why we found the boundaries for the y. Now those boundaries, these boundaries here, are going to go as our boundaries on our integral. So it's going to be from negative square root of 4 minus x squared over 2 to positive square root of 4 minus x squared over 2. Okay. The thing that we're integrating here, that's our f of xy. 4 minus x squared minus 2y squared. Now, what about our outer boundaries? So to find the boundaries for y, we let z equal 0 and then solve for y. To find the boundaries for x, you need to let z and y equal 0 and solve for x. So let's let z equal 0 and y equals 0. So if I did that in this equation, then I would have 0 equals 4 minus x squared. Okay. So then I would have x squared equals 4. So x equals plus or minus 2. So that's our boundaries for our x. -2 to +2. Alright, so if we first integrated with respect to y, we would have integral -2 to 2. That's going to be 4y minus x squared y minus 2/3 y cubed all of that is going to be evaluated from negative square root of 4 minus x squared over 2 to positive square root of 4 minus x squared over 2. And then I have dx. Alright. Now this algebra is, I guess, a little tricky here. The easiest way to evaluate this, you have a y here to the first, you have a y here to the first. Believe it or not, the easiest way to evaluate this is going to be to think of this function like you had 4 minus x squared times y. That's what we would get if we factored a y out of those two, minus 2/3 y cubed. Let's see what that gives us. Alright, so we would have four minus x squared. Now, I have to plug in, I didn't put my boundaries here, I probably should have, but I have to plug in this to this, which you might want to think of that as, this right here is the same as negative square root of 4 minus x squared, which you could bring that negative out, times, that's going to be 1 over the square root of 2, or square root of 2 over 2. So you could write it like that if you wanted to. You could even take that a little bit further, and instead of having that square root, write that to the 1/2 power. And so this top boundary would just be square root of 2 over 2 times 4 minus x squared to the 1/2 power. That might make that a little bit easier for us to calculate if we do that. So I have 4 minus x squared. So I have to plug in the top boundary minus the bottom boundary. Alright. So this is going to be, I'm going to plug in the top boundary first. Square root of 2 over 2 times 4 minus x squared to the 1/2 power. So that's plugging in the top boundary right here. And then I would have minus 2/3. Now, if I plug all of this in and cube it, then let's see, square root of 2 over 2 cubed, without simplifying, that would be the square root of 8 over 8, which that can be simplified. And then whenever you cube this term here, it becomes to the 3/2 power. Okay, so that's what I get when I plug in the top boundary. Now when I plug in the bottom boundary, remember I just have to subtract all of it. So it's going to be minus, and then plugging in the bottom boundary is going to make the first term negative, right? I'm going to have 4 minus x squared times negative square root of 2 over 2 times 4 minus x squared to the 1/2. And then I'm going to have, let's see, whenever I'm going to have minus 2/3, but then let's see what happens. Since I'm plugging in a negative and cubing it, I'm going to get a negative out. And so that's going to be a plus because there's already a negative in front right here. Same, square root of 8 over 8 times 4 minus x squared to the 3/2. All right. So we are subtracting, and I left it like this because we are subtracting these two terms. And so there was a negative here, so if I distribute this negative to this term, it becomes positive. Right, so this term is going to become positive, and then if I distribute this negative to this term, it's going to become negative. Okay, so I've distributed those, and now notice that, let's see, what do we have left? I guess first of all, to clean this up a little bit, I don't think those terms are going to cancel out. So we had positive, negative, and then whenever we put this like term, that made that positive, negative. However, these are actually all like terms because look, whenever you say this term times this term, you get to the 3/2 power, just like this term. Right, because 1 plus 1/2 is 3/2. So all four of these terms are like terms. Let's see if we can clean them up a little bit. Alright, so that's going to be, I have square root of 2 over 2 and square root of 2 over 2. And these are both going to be 4 minus x squared to the 3/2. The square root of 2 over 2 plus the square root of 2 over 2 is 2 square roots of 2 over 2, which is just the square root of 2. So it's the square root of 2 times 4 minus x squared to the 3/2. And then this is minus, that can be simplified. That's 2 square roots of 2 over 8, or square root of 2 over 4. Alright, and then whenever you say that times 2/3, that becomes the square root of 2 over 6. So we have a negative square root of 2 over 6 and a negative square root of 2 over 6, right? Because of the negative in front. So negative square root of 2 over 6 minus square root of 2 over 6, that's negative 2 square root of 2 over 6, or negative square root of 2 over 3. Alright, so that's just going to be negative square root of 2 over 3 times 4 minus x squared to the 3 halves dx. I didn't put my dx there, but still dx. So, to simplify this a little bit further, since they both have that same term in common, we can do a little more algebra, and we can factor this term out. So it'll be 4 minus x squared to the 3 halves times, what would that leave us with? Square root of 2 minus square root of 2 over 3. dx. So put this both in terms of thirds. That would be 3 square root of 2 over 3 minus 1 square root of 2 over 3, or 2 square root of 2 over 3. Alright. So now we need to integrate this. So that's a constant. You can factor that out. 2 square root of 2 over 3 times the integral from negative 2 to 2 of 4 minus x squared to the 3 halves. More than likely you don't remember how to do that integral unless you have been practicing your integrals from calculus 2, because this is one where we have to use a trig substitution. We go back to chapter 8. Let's see, trig substitution. So we have a squared minus u squared to the 3 halves. A squared minus u squared. So with a squared minus u squared, we say u equals a sine theta. So that, this right here is the stuff we need. Look at the boundaries for theta there whenever you change it over. Negative pi over 2 to pi over 2. As we're changing this over to trig, we're going to have to also change over our boundaries. Before, what we did with an indefinite integral, we changed it over to trig, then we used the triangle and we changed it back to algebra. Well, it would be easier if this is a definite integral to just change our boundaries and evaluate it at those new boundaries, since it's a definite integral. You could change it back, but it's quicker not to change it back, believe it or not. The thing that gets me on this integral is, you can see how long it's taken me to work this integral. Your book works it out in about 6 steps. They just don't explain anything that they're doing in the book. They kind of do, but then they kind of don't. They just put little side notes. All right, anyway, so let's just continue to work on this problem so we can actually get the fulfillment of working this problem completely. Maybe, maybe not. I don't know. This integral looks very interesting because, all right, so we would have x equals, what's a in this problem? 2. So 2 sine theta. So if I plug it in right here, oh, also dx equals 2 cosine theta, d theta. That's where we get our d theta from. All right. So this would be 2 square roots of 2 over 3 times the integral. And we're changing over to theta from negative pi over 2 to pi over 2. What is all that in there going to become? We're going to have 4 minus, that's going to be 4 sine squared theta to the 3/2 times the dx. I'm sorry, the dx is 2 cosine theta d theta. Okay. So this right here is 4 times 1 minus sine squared theta. And all of that is to the 3/2 though. That's the thing. So this 4 is to the 3/2 power. I'm just trying, since we have a product and we have a power, we can take and apply this power to each one of those terms. And also this right here, that is cosine squared theta. So 4 to the 3/2 is the square root of 4 cubed. The square root of 4 cubed. Square root of 4 is 2. 2 cubed is 8. So I can take that 8 to the outside. What is the square root of cosine squared? That's just going to be cosine, then raised to the 3rd power be cosine cubed. There's a 2 on the outside and there's a cosine on the outside. So I can bring this 2 out. This right here was going to be cosine cubed, and that's cosine to the 1st. So this is the integral of cosine to the 4th d theta. All right, so so now we have to integrate cosine to the 4th, which is cosine squared squared. The reason why I say cosine squared squared, it's cosine squared squared, because we have a formula for the integral of sine squared or the integral of cosine squared. It's from your trig formula sheet. Do you remember that one? What do we have to make this? The power reducing formula. It's 1/2 times 1 minus cosine of what? 2 theta. So what that does is that reduces this power. But it's all of this squared. Okay? So that's going to be 1/4. That's going to be 1/4 that I'm going to bring out. Then times the integral of, whenever you FOIL this out, you get 1 minus 2 cosine 2 theta plus cosine squared 2 theta. Right, because whenever you say this thing times itself, you get cosine squared. So this is another one where you have to apply the half angle formula, or the power reducing formula. And so that term is 1/2 times 1 minus cosine 4 theta. Okay. So we already had, for some reason I got rid of this here. We're going to have to, that's going to be 4 times 8. It's going to be 32. So that's 32 square roots of 2 over 3. All right. The only other thing that I'm worried about is integrating from negative pi over 2 to pi over 2. That might actually cancel out. If it does, we'll go back and integrate from 0 to pi over 2 and then say the answer times 2. So we'll see. We can always just integrate from 0 to pi over 2 and say it times 2 at any point because of symmetry. This object is very symmetrical. All right, so we plug that in. So right there, you imagine that's 1/2 minus 1/2 cosine 4 theta, because you have another constant in front here. So you can put this 1/2 and that 1 together. Also, I'm going to cancel that out. So I have 8 square roots of 2 over 3 times the integral from negative pi over 2 to pi over 2 of 1 that's 1 and 1/2 is 3/2. So 3/2 minus 2 cosine 2 theta, and then minus 1/2 cosine 4 theta d theta. Alright, so that is 8 square roots of 2 over 3 times, that's going to be 3/2 x, or theta, excuse me. The integral of this, the integral of cosine is sine, so bring out a 1/2 because of the du, so it's going to be minus sine 2 theta. Same here, I need to bring out a 1/4. So that's going to be minus 1/8 sine 4 theta. And now this is evaluated from negative pi over 2 to pi over 2. Here's the moment of truth where let's just hope that that we can get an answer out. I think we can. Let's see. All right, we're almost done. All right, so I have 8 square roots of 2 over 3 times, plug in pi over 2. 3/2 times pi over 2 is going to be 3 pi over 4. So I have 3 pi over 4 minus the sine of pi. Sine of pi is 0. Minus 1/8 sine of 2 pi. The sine of 2 pi is 0. Then I have minus, I'm going to plug in this bottom, so I have negative, so it's going to be negative 3 pi over 4, and then minus the sine of negative pi is 0, minus 1/8 times the sine of negative 2 pi. Maybe I can get a little more room there. Let me write that smaller. So that's minus sine of negative pi minus 1/8 sine of negative 2 pi. All right. So that's 0, that's 0, that's 0, that's 0. So I have 3 pi over 4 plus 3 pi over 4. That is 6 pi over 4, or 3 pi over 2. So I have 8 square roots of 2 over 3 times 3 pi over 2. Looks like that and that cancels out, that and that. So I have 4 there, so that's 4 square roots of 2 times pi. That's my volume. Alright, very satisfying to work through all of that and get the right answer. I'm going to show you how the book works it out really quick. So you see how we worked it out. Alright, we started out, we bound our integral. We had to do a lot of algebra to get it down to a form. When integrating, we had to use trig substitution. When we used trig substitution, we had to adjust our boundaries. And then we worked it out and we got the answer. And so here's what the book does. It basically does the same thing. You can see here, they set up the integral. Well, they integrated and then there was no explanation to get to this point. So you just have to know how to do the algebra to get to this point. Then they used trig substitution. And then instead of working out the integral using the power reducing formula twice, they used this Wallace's formula. It is in your book as well. It's just a way to work out a cosine to an even power. So that's what they did. But they got the same answer. So that's the main thing. All right. So you can see right here, look at the dx here. It shows us we're taking all of these rectangles and summing them up. That's what we did last. So that's kind of interesting. So of course every problem that we work couldn't be that long. But Wallace's formula is also in 8.3. It's 8.3 or 8.4. The easiest way to work that out, though, is if you have a calculator that's capable, is to plug in that very first integral and then just hit equals. You know, of course, the calculator will work all that out for you. Let's look at this next example. Comparing different orders of integration. I'll show you the figure as well. This is on page 980. So there's our surface bounded by the planes x equals 0, y equals 0, y equals x, and x equals 1. And here's the figure. Here's what the figure looks like. So you can see the surface here. Here's the surface. What these planes do, though, is they chop that surface in all these pieces. So we have z equals 0. That's the xy plane. Y equals 0 is the xz plane. So this plane on the back side here, you know, with this coming out that way, that kind of like the back wall you could think of, that is y equals 0. Y equals x is this line here. So it would be this line, but then extended up forever and down for it. Well, I guess it can't go below the xy plane, so that's why it cuts this side off like that. And then x equals 1. X equals 1 is this line here. And so it cuts the figure off from coming out anymore. And so when you bound it by all of those different planes, then you get this figure here. All right, so if we started out and we tried to set this up the exact same way, a double integral of f of xy dA, and we decided dy dx, or if we decided dx dy, it would make a difference. Because if we decide, let's see, if we decide dx dy, let's see what we would have. So dx dy, and if we decide dy dx, let's see what we would have. Dy dx. So let's compare these two orders of integration. Now we have our surface, so our surface isn't going to change. Our surface is the same for both integrals. E to the negative x squared. All right. So if we look at this thing, if we let z equal, let's see, let's try to imagine what this would look like in 2 dimensions. If we were just looking at this in the xy plane. So like, we're just looking at it, so here's the y. Well, I guess we would be looking at it back on the back side. But it would be kind of a triangular region. So if we were looking at it from the side, and this again is on page 980. Don't worry about the z. Don't worry about the actual surface itself. If we were just looking at this in 2 dimensions, then we would have 2 choices. We could set this up dy dx or dx dy. Now it already has the boundaries for us here. You can see if we were to bound this thing, the y, between 0 and x, then this would be the integral. And then how do we get the x values? We let y equal 0 and get the x values. Or if you were just looking at the picture, you could tell what the x boundaries are here to here. Now, if we bound this thing with the x, then we integrate from y to 1. And again, the boundaries for the y would be the y boundaries, so it would be here and here. Now, the problem with the second integral is that that's not an easy integral. You can't integrate e to the negative x squared. That's not an elementary function. You don't have the du. So there would have to be some other way to integrate that. However, if we integrate with respect to y first, then this would be y e to the negative x squared, evaluated from 0 to x. We'd still have this integral out here. And so now if we plug in the x for our y, that would be x e to the negative x squared, and then plug in the 0 for the y, you get 0. So you end up with an integral, this integral here, now that you can do. Because if you let your u equal negative x squared, your du equals negative 2x, and you have the x in front. The other way is just not doable by any easy process. You might could look at the tables, maybe your integral tables or something like that. Yeah, your calculator can probably do it, but we end up getting, and you may want to work through this integral here, you end up getting e minus 1 over 2e. Okay? That's where we'll pick up on Wednesday.